I'm David Jenkins, graduated from UC Davis with a BSEE. I've always loved electronics, I've always loved building things, I've always loved designing things, and I've done a lot of it. As a freshman or sophomore, somehow I got interested in continuous wave nuclear magnetic resonance detectors. So that was my first introduction to the real physics department, where I learned from brother Eric, who was completing his doctorate, for some reason, going back to his seminary. And the first detector I saw was continuous wave. It was built from a device that glowed in the dark and would burn your fingers if you didn't turn it off for a while. Well, I was newbie kid on the block. I liked transistors. I built a transistor detector based on his instructions for his vacuum tube detector. It worked. It's fascinating. My first little project. Here I'm a freshman in college, and I'm doing NMR work. So that's carried me all through my life. When I graduated, I stayed at the chemistry department as an electronics technician because I loved experimentation, I loved building research instrumentation, and as most of you know, almost all research is based on instrumentation of one kind or another. I was very popular in my department. In fact, I was so popular there were people in other parts of the UC system like San Francisco would call me if the department head approved it, I could build instrumentation for them. Well, 4 years into my ET experience, and here I am, I'm a big frog in a small pond, because what does a chemist know about electronics? I could answer lots of questions. I could do almost anything that they demanded of me. And microcomputers came out, which you could buy a personal microcomputer for $500. This meant that any hobbyist could jump in and get experience with running a digital computer. And I immediately saw that that was the future. So in my spare time at night, I designed several input-output boards, because the computer you got for $500 was a box, a power supply, and a CPU, and nothing else. So I built input-output boards for the computers, so I was selling them at night. I was making more money at night than I was at my day job. So a fellow in Sacramento had a small business. He saw the immediate future in microcomputers. I joined forces with him. He made me a small partner in his company, and I immediately learned what it's like to go from academia into private business. It's not easy. You're responsible for meeting your employee's salary, whether or not you've got the money to pay them. So working 12-hour days and greeting my kids at night by kissing them goodbye or kissing them goodnight, and then spending the rest of the day and the weekends at work got on me eventually. So I became a consultant. So I consulted in electronic design for about 18 years. Some of the things I worked on, early in the 80s, there was a company called Compression Labs in San Jose, California, which is the center of Silicon Valley. They were doing compression of real-time television, running it through a couple of wires to a decoder, rebroadcasting it, and you could not tell the difference in quality between the original image and their reconstructed image. I worked on the decoding end of things because they had a special processor for their encoder. Their processor for encoding was 4 specialized chips closely connected physically, surrounded by high-speed memory and analog to digital conversion. That is now replaced by your cell phone. Your cell phone can take real-time video, and it's all done with chips that are fallouts from this type of compression and encoding experience. I worked in the defense industry on what was Ronald Reagan's Strategic Defense Initiative, commonly called Star Wars, which I think was his critics were trying to criticize him for being stupid and doing something that was impossible. Let me tell you, it was very possible. It was the bleeding edge of technology. It was very expensive work. There were a lot of people involved. In fact, it was so complex that the security, while not non-existent, wasn't enforced very much because they figured no one person could ever know all the details of what was going on. I was working on developing a 6th degree of freedom inertial measurement unit. Now 6 degrees of freedom means you have 3 accelerometers, X, Y, Z axis, so you know physically where your device is moving. This was made for satellites. It was going to be on a satellite, so it needed to be small. And you have 3 angular rate sensors, which tell you your roll, your pitch, and your yaw of your vehicle. That was going to be the size of my thumb when we were finally done. And when we were starting, these rate sensors and these accelerometers are about the size of my fist. So we were taking what was essentially a very complex electromechanical device, converting it to solid-state electronics, including all of the processing, and there's a lot of mathematics goes into a solid-state device, and putting it out at a very small size. You can do that today. You go into a toy store for $29, you could buy a helicopter that has a 3-axis solid-state gyro built into it, for 29 bucks. That's the fallout from Star Wars. Star Wars was real. Anyone who says it wasn't is a moron. Sorry. Yeah, I get kind of upset. I worked on it, I know. Let's see what else I wanted to mention. I worked on high-resolution imaging for satellite. It was primarily satellite imaging. It was, this wasn't directly a Defense Department project, but the company I was working for did have contracts to provide high-resolution image. At the time, the limit on film imaging was 4,000 lines per inch, and we did it. We produced an imager that could do 4,000 lines per inch, so you could make film out of the satellite transmissions. One other thing I wanted to discuss was UC Davis was in a collaboration to build a high-sensitivity X-ray detector. They originally intended it to be used for mammograms. With a high-sensitivity detector, you could turn down the X-ray intensity very low, so there'd be much less exposure to the human body, and then it would be much safer, obviously. I designed some of the initial prototypes. I actually laid out the integrated circuit, telling the silicon foundry where I wanted, particularly doped layers, how I wanted them interconnected. I designed gates and flip-flops and such to support the circuitry. I'm happy to announce that that is now in a detector setup at the Large Hadron Collider at CERN. So when I started preparing this talk, I thought, I've actually been involved in quite a bit of stuff that's now just commonplace, everyday use. So I went into business after my consulting, became a partner in a small company. We sold the company in 2007. But in the meantime, about late 1990s, early 2000s, someone mentioned a guy named Woodward at UC Fullerton who'd built this little device that had a unitary thrust. I thought, wow, that sounds interesting. Let me look into it. I found a detailed documentation that Jim had made on what he had done to do this experiment. I thought, as an E over C squared equals M is a piece of cake. All I needed to do was duplicate his setup and I could make the thing work. But unfortunately, being a wonderful experimenter, he's also a wonderful scrounger. The parts he used were no longer available, so I had to go find some company that could provide a piezoelectric actuator that would be similar to what he had. What I found was much higher frequency. I looked for the highest energy per mass capacitors I could that had low loss. I put the setup together. I built myself a little balance. This is not normally something an EE would have. I used an aluminum beam. I had it mounted on a razor blade for a fulcrum. I had a front surface mirror, which I shone a helium neon laser on, so I could get reflected laser light, 10 feet away, as Jamie was talking about. Had a null result. At that point, I said, clearly the mathematics is good, the electronics is good. I had duplicated everything. That's a piece of cake for me. I had phase shifting. I had double the frequency because your capacitor running with a pure sine wave has 2 energy peaks per cycle of a sine wave. And so your actuator only has one peak motion. So I had all of those things electronically figured out, no result. What I decided was, I'm a firm believer that it's real, but I need more instrumentation such as a laser interferometer, which at that time was not available readily. And I didn't want to spend all the time and effort building it. So that's how I got excited about Jim's device. I'm still a firm believer in it, and now I'm designing a more efficient driver so that you can move the process down a little bit. But I want to briefly touch on John's talk last night when I said that SETI is a joke. It's a silly effort to investigate, and I'll explain why. They're looking for...
What is a joke?
SETI. Oh, the search for extraterrestrial intelligence. Okay. This is why, from an EE, believe me, I've got the experience. I know what I'm talking about. They're looking for a continuous signal. For a TV signal it might be 800 megahertz, but it's steady. It's there all the time. For us, it's 24 hours a day. Same with an FM radio station, lower frequency, but it's there steady all the time. An AM radio station on your car radio is there, and it's steady all the time. What SETI does is they have a multitude of receivers which are very narrow band. Now the reason you want narrow band is because you're looking at a signal which is going to be nothing compared to the noise background. In fact, I can't understand how the path loss wouldn't be so great they'll never hear anything beyond a light year. Anyway, so they look around a very narrow band. And if they see something, okay, it's great. But the problem is, here's what I think has gone on. In World War II, there was a famous starlet in Hollywood named Marlene Dietrich. And in her off hours, she was a brain. She was a brilliant person. She went to the Army, I believe, before she got her patent. She said, look, we all know that the opposing forces are copying all of your radio messages. Why don't you do the following?
That was Hedy Lamarr.
Was it Hedy Lamarr? Yeah. Oh, I was thinking it was Marlene Dietrich. Yes. I'm sorry. I'm sorry, Marlene. She had the right country, though.
The first naked actress in
Absolutely, the first naked actress.
She was not a starlet. She was a starlet.
She was not a starlet. She was a starlet. She said, look, you're broadcasting, we'll just say, for example, you're broadcasting all of your information to your troops on 7 megahertz or your intelligence information. The enemy is copying that. He'll eventually figure out how you've encoded it. He'll decode it to get your message. He says, why don't you broadcast for a short time on 7 megahertz, change to 6 megahertz, broadcast again, go to 8 megahertz, go to 4 megahertz. It was called, well, now it's called spread spectrum. Back then it was just called crazy. She got a patent, no one borrowed it. So 75 years ago, she had this idea for spread spectrum. So now a very famous book writer in this audience has written a little appendices where he has Alice and Bob talking to each other over an entangled communication network. So what I'm going to propose is Alice and Bob have decided they're going to use spread spectrum communication to talk to one another. So this is a very simple diagram of what's going on. At a period 1, as the transmission starts, Alice and Bob have agreed they're going to transmit and receive on frequency F1. At period 2, for example, they may transmit and receive on frequency F3. At period 3, they may be down to frequency F2, and at period 4, they'll go frequency F4, and the cycle repeats. Now remember, this is just simple. Now, suppose Carol and Jim want to talk about a romantic evening in Estes Park. They want to transmit in the same frequency band. So they've agreed in advance on what sequence they're going to use for their transmissions. So they may start on their first interval on F4. Their second interval might be on F1. The third interval might be on F3. And then their fourth interval is going to be on F2. Now note that there are 2 channels of communication that are ongoing. They're completely independent from one another. They do not interfere. And I'll get even further. Now suppose Pauline and John want to start a conversation. So they'll just agree in advance on a sequence, and they'll know what the other 2 are using because they're friends. So they'll start on F2. They'll go up to F4. They'll go down to F3. Whoop. Oh, F1, there we go. And finish up on F3. Now suppose Amy and Tony want to converse. They're talking about Marshall Space Flight Center is the best place in the world to work. So they want to start a conversation. So they may start on F3. They'll go to F2. They'll go to F4. And to finish up, let's see what I do wrong here.
F1.
Oh, F1, there we go. Okay. Now if you didn't see the X's, the squares, and the circles, what pattern do you see there that can resemble any kind of communication with intelligence? Nothing. What this looks like to the receiver who doesn't know what to tune is noise. It's like you have a wind chime. You put a wind chime out in the wind, which is fairly arbitrary and capricious and random, and you'll hear the chimes. You know, maybe you may have 3 chimes, you hear the chimes. You take the wind chimes away, and your ear will hear nothing but noise. There is no distinguishable frequency that you will hear. Now take this and multiply it. Say you've got 1 million frequencies, all within today's technology. It could be 100 million. But just for convenience, go to 1 million. Go to a sample size of 1 million random samples. If you get a truly random assortment, which you could get by, you could time radioactive decay, you could time cosmic rays, you could time lightning strikes. What those are unpredictable events, completely random events. No computer in the world can decode a random event because by nature, by definition, it has no pattern. That's why I say SETI looking for this is absolutely ridiculous. We've done this for maybe 100 years. We've known for 75 years that we could use spread spectrum, use more communication, more people, non-interfering, and undetectable. That's why I say I think SETI is ridiculous. An advanced civilization is going to be doing something like that. Yes?
Aren't they also looking for things like high-power radar, their scientists mapping
Yeah.
the system and stuff?
Jim asked me that last night. You don't have to have a continuous wave for radar. You can go to a chirp method. You can go to, there are any number of methods to avoid having any detectable signal. In fact, I would be surprised if the Defense Department isn't doing that to avoid air-to-ground missiles destroying their radar sites.
So
John.
I think that not only is sufficiently advanced technology indistinguishable from magic, it's indistinguishable from noise.
That's right. That's exactly right. Exactly right. That's why it's my theory the microwave background radiation is half other life communicating with one another.
And there is another reason, which has to do with compression. The more you compress information, the more it looks like random. So it's actually a very primitive civilization that would look like a pattern. And if you compress an image, like a JPEG and so on.
Well, see, though, actually, as you compress something, well, if it's non-random, you can compress it. But then you start to get a pattern because your compression is now fewer bits that have been encoded.
The compression key looks like noise completely. That was, Stephen Wolfram was the one who came up with that theory that aliens are communicating via compressed.
They certainly could, sure.
And since we don't have the compression key, it looks like noise.
Well, they could be using burst technology, you know. Each of these dots, the time period between these could be nanoseconds. This could be a burst at a frequency, with maybe 1,000 bits. You could encode this. Maybe this is encoded based on the phase of the frequency that you're sending. So you divide that phase into 90-degree increments, 0 to 360 degrees, 90-degree increments. Each increment could represent maybe 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So now on each bit of transmission, you've sent out 2 data bits. But there's a whole...
Any tax dollars going into this city?
Is there what?
Tax dollars.
No.
Oh, no.
Good.
Oh. I was just thinking, if 1% of the money that has been spent on SETI were spent on Jim's device, we'd have a device floating off the table.
If Paul Allen spent $60 million, you got a Russian guy who's putting like $30 million.
So what was that?
You had Paul Allen put in $60 million.
Yeah.
You had a Russian guy.
Jim ought to talk to Paul. Maybe hire Seth Shostak. He's a good salesman. Okay, now we'll get to the real talk. Alrighty. So I was very excited about Jim's device. I think it's extremely practical. I think what's needed is better information on what exactly is going on physically, because all the mathematics looks good. It looks very solid to me.
So even though you got the null result, and you're still excited, what's exciting
Yes.
was that the theory was strong.
Yes,
Compared to other ones.
that's correct.
Okay.
That is correct. I've investigated a lot of crazy stuff when I was retired. I traveled around the United States trying to talk to inventors who wouldn't open their doors or had left the country. So Jim was easy to contact. I don't remember how I contacted him at first. Got onto his mailing list, got very excited, went to the Estes Park workshop 2 years ago, got excited, and at the aerospace last year I decided I want to do something to try and contribute rather than just being a leech listening to everybody else. Although it's fun listening to you, Jose. whether you're an active participant or a
What are
speaker.
the statistics on words spoken by who at this time?
What's that?
What are the statistics on words spoken by who at this conference?
Oh, yeah, good question. Oh. Okay, so I have come up with, let me see what I did start with. Okay, for fun, I do crazy things. I wanted to recreate a CW NMR detector for fun to see. My friend of mine does extreme sports. I thought that maybe if you could just analyze maybe some sweat, put it through an NMR to determine at some really crude scale what's going on with the sweat, you to determine when someone is exceeding their body's limits on extreme sports, because these guys are usually wrecking their bodies with the exercise they're going through. So I built a little NMR detector. These are ferrite magnets, RF coil to detect the NMR resonance, little sample holder, which was a lead pencil container that was very convenient. I got a deck with some baseband filters to filter it. I've got an RF board to excite and receive. I've got a detector, which is DC coupled, so I could go to really low frequencies, which I'd probably never see. If you know NMR, you know that ferrite magnets, the homogeneity is pretty crude. I just wanted to see what I could observe. NMR itself is extremely sharp. It needs homogeneities that might be 10 to the minus 4 Gauss. I used to play and adjust those when I was an electronics technician at the chemistry department, because that was, the basis of a lot of their studies. That's fun. I have electronics all over my house. Does all kinds of things. This is pretty much a block diagram, a very simple block diagram of what Jim Stresser experiment is doing right now. He's got a signal generator. It drives a power amplifier. The power amplifier has to have an LC matching network or some kind of matching network, and then the piezoelectric actuator. The signal generator, generates your signal, but it's a very low power device. It might have an output of 100 milliwatts and an output resistance of 50 ohms. The piezoelectric actuator, depending on what type you're using, might have a apparent resistance of 10 ohms or 10,000 ohms. So you need to be able to, and a power amplifier, I'm using a Nico stereo power amplifier, which it's optimized for an output load of 8 ohms. So the matching network then has to take the capacitive reactance, the apparent resistance of the actuator, convert that down to an 8 ohm resistive load so the amplifier can adequately drive it. Now the problem with that, of course, this is the amplifier I use. It's a Nico super duper stereo amplifier. It's good for 100 watts continuous RMS per channel. I measured the bandwidth 10 hertz to 65 kilohertz because I wanted to make sure it was going to cover Jim's frequencies of 40 kilohertz when I was playing around with my testing. This is a diagram of a very simple LC matching network. This one is designed for maybe high frequencies, maybe half a megahertz up to 30 megahertz. Has a variable input capacitor, a variable inductor, and a variable output capacitor. Now the advantage of that is you can balance and negate any reactance in the output within limits and transform the resistance into something that looks like a resistive input for your amplifier. Now the biggest problem with this is the size. For a 10 watt enclosure, the size might be 600 cubic centimeters. For 1,000 watts, it might be 12,000 cubic centimeters to do the job right. There's no limit on frequency that these could be. Oops. There we go. This is a one I made for myself to fool around with. This is good for 25 watts. As you can see, it's about 18 centimeters wide. It's probably 8 centimeters high and maybe 12 centimeters deep. It can transform an output resistance. I use it for a long wire antenna, 10 ohms to 5,000 ohms, almost any kind of crazy reactance. I wanted to test the efficiency of a linear amplifier. Now, when Jim's device is in a spaceflight regimen, there's going to be a limited supply of energy. So therefore, you want to maximize the energy flow and minimize the energy loss. So I've taken, this is a pure sine wave generator. It's based on resistive capacitive network So it's very, very linear. It drives my Nico audio amplifier. It drives a 0.5 ohm resistor because audio amplifiers are not designed to drive a pure capacitance. And the capacitor I chose is 1 microfarad because that's very close to what Jim is going to be using on his new actuators. This is what's called metallized polypropylene. It's extremely low loss. I wanted to see, if I could transfer the energy in and out of a pure capacitor reasonably well. I set it up so I measured the RMS voltage across the resistor. I knew the current, and I could know the RMS voltage and calculate the peak voltage and the peak energy in the capacitors. I adjusted the output so that it was about 20 watts circulating in and out of the capacitor. At 10 kilohertz, the efficiency, I measured the input power consumed by the linear amplifier with a power meter connected to the 115 volt 60 hertz. And this is a reasonably accurate, I've measured the accuracy, it's 1 or 2%. More than enough. All I wanted to know is just how crude the linear amplifier was. At 10 kilohertz, at 20 watts, the efficiency was 35%. At 20 kilohertz, where the capacitor has half the reactance, the efficiency was 23%. Now the problem is, in a linear amplifier, the output transistors have to dissipate the difference in voltage between the supply voltage and the output voltage. So when there's very low output voltage but high current, those transistors are just burning up all that power. The other thing is, the linear amplifier does not recycle any of the energy coming back from the capacitor. It has to dissipate that. So I had an idea. What if I used current MOSFET transistors as switches and I charge a capacitor through an inductor? That's an extremely efficient way to charge a capacitor. And after a certain amount of time, I open the switch, the inductor discharges through a diode to ground and continues charging the capacitor. When it's time to discharge the capacitor, the reverse happens. There's a MOSFET that turns on to ground. The inductor charges, the capacitor discharges trying to charge the inductor. At another time interval, that MOSFET 2 opens up. The inductor discharges into the supply, returning the energy from the capacitor into the supply and continues to discharge the capacitor. Now MOSFETs act almost like a perfect switch. When on, they're much less than 1 ohm of resistance. And when off, they can be greater than 100,000 ohms resistance. Very low current flow when they're off. So the energy in the actuator capacitance would be recycled. A similar situation happens if you want to drive the capacitor in the opposite direction. Now you have other MOSFETs. These are MOSFET 3 and 4, which do the same thing. Charge a capacitor, reverse through an inductor, discharge, etc. This is the block diagram of what I've come up with. And I almost built, but when it came time, 2 months ago I decided I better write my paper first and then finish this. Right now it has about 547 components. We have an analog signal input, a low-pass filter. Now in any sampled system, you have to be careful that the signal you apply to the sampled system is less than 1/2 the sampling frequency, or you generate what's called aliases, which look like real signals. I mean, the output doesn't know the difference, and it'll clearly would destroy any kind of fidelity on the output. There's control logic in a field programmable gate array. I always like creeping realism. I can never leave anything alone. I've added a direct digital synthesis frequency generator on board, which can be selected via the user interface. This is readily available from analog devices. It's like $8 a piece. It runs off a quartz crystal oscillator, so it's extremely accurate. It has 28-bit frequency registers, which means it has better than 1 hertz resolution from less than 1 hertz up to maybe 10 megahertz, although Jim will probably not go much above 100 or 200 kilohertz right now. There are error amplifiers. The error amplifiers compare the output across the actuator to the analog signal that's been applied. If there's an error, the logic knows which way to control the output transistors to either increase the voltage on the piezoelectric actuator or reduce the voltage. There's a user interface. I've got a liquid crystal display. It's 4 lines. It tells the user what's going on. It measures the peak current in the actuator. It measures the peak voltage. And it allows him to adjust many of the parameters that are then sent to the control logic to change how the unit responds. I've got push buttons for manual entry of small numbers. I've got a rotary encoder for entry of, the 28-bit number takes a long time if you're pushing a button. So the rotary encoder allows you to quickly increase or decrease the numbers, and the user interface displays what you're doing on the display. The crystal oscillator, which is a master oscillator, provides very stable timing. Not all of the interconnections are shown because it's a little more complex than I've shown here. The low-pass filter, as I say, it's an anti-aliasing filter. You've got to keep the filtered signal from being close to the sampling frequency. This is a 4-pole, it's called 0.5 dB Chebyshev response. 0.5 dB means that it's in its passband, the amplitude of the output will not vary by more than 0.5 dB, which is going to be plenty for Jim. Chebyshev is a faster fall-off characteristic, which makes sure the high frequencies, which you don't want, are very successfully killed. Right now, I've set the cutoff frequency 3 dB. 3 dB is called the cutoff frequency, where the response is now down 3 dB to 200 kilohertz. My sampling frequency to start with, because this is all preliminary, is about 2 megahertz, so I have plenty of room to increase that as needed. This is the error amplifiers and comparators, which tell the control logic what's going on between the input signal and the output actuator. We have a sample from the filtered signal input. We have an output sample, which comes right off the output of the at the actuator. We have a positive error, we have a negative error, and we have what's called a ramp. Now what this ramp does is this allows a pulse to be generated if there's a positive error, which may be 0 to maybe half of the 2 megahertz switching frequency, and similar with a negative error. And allowing for a variable pulse width allows this to be a much more linear amplifier of the input signal. I wanted it to be very true to the sine wave. And there are conditions which compare the input to the output. Signal is greater than the input, the output's greater than the signal, output's less than a positive threshold, output's greater than a negative threshold. These thresholds I set because if you've gotten 95% of the energy out of the capacitor, it's a waste of time to keep sampling down until it's 0. So it just tells the control logic to quickly go to the next setting required to follow the input signal. Then we have a signal greater than 0, output greater than 0. These are some waveforms of what's going on. The output always trails the signal because it has to know what to do to follow it. I've shown this as much more than it is. It's probably going to be maybe 1 or 2 microseconds trailing it, which won't make a big difference. It'll be constant at least. So if you have a phase adjustment, it's not going to affect it much. This is what the ramp looks like on an oscilloscope. It starts at 0, goes up to some value, and then goes back to 0 and repeats itself. And this is the typical drive pulse. If there's a small error following the signal, then this little pulse which drives the output transistors is short. If there's a large error, then this ramp and sample puts out a drive pulse that's much larger, so the output is going to catch up to the signal input. Now, I've added, because I've obviously been talking to Jim, I've added a DC offset, which in this case is shown as a positive offset, so that you get 1 energy peak per cycle on a sine wave, if that's what you want. It can be 0, it can be negative. So you can actually reverse what's going on to see what the effect is on the experiment. And that's all user programmable. The user interface tells you what that is that you've set. This is a simplified picture of the logic on the field programmable gate array. We have all the outputs for the error amplifiers and the signal status comparisons. This is a little field programmable gate array, which means that you can reprogram it as you need to. That's almost unlimited number of times reprogramming it. It has 5,280 lookup tables, 5,280 flip-flops, which means that it can do a heck of a lot of processing on its own. And in fact, you can load it to be a simple digital signal processor with the right intellectual property. It has built-in RAM, 1K bits of RAM. It has block RAM if you need to store things temporarily. It has a 16 by 16 bit multiplier with a 32-bit accumulator. It has 2 I2C, 2 SPI control inputs. And as I say, this can be reprogrammed by the user, or allow the user to be able to go in and reprogram it. So if a grad student wants to do something really crazy, he can go in and he can reprogram how the control logic responds to input signals. I've shown 3 outputs to drive 3 different sets of bridges, because one of our esteemed members has been doing an experiment which requires 3-phase outputs. So I wanted to make sure that he'd be covered if he needs to do that. Then this detects current errors and it outputs the ramp generator signal. Now this FPGA, as it's called by short, can be programmed with software that's specially designed to do that programming. This is a sample of a logic program which takes a clock divider. If it's equal to 287, it says set the divider to 0, clear the divider, tell the end of cycle it's over, send a pulse out which says it's the end of a cycle. But if the clock is 284, set the end of cycle to 1. Or if the clock is 142, say it's the last half cycle of this particular phase of the operation. And if none of those are true, then it says take the clock divider and add 1 to it and set the new clock, set the last half cycle to 0, set the pulse out to 0. So this started out as what's called VHDL, very high density logic programming language. It's now evolved into what's called Verilog, because VHDL was not manufacturer specific, so manufacturers couldn't prevent you from using the code on some other manufacturer's components. This is my impression. But every manufacturer of logic parts provides the software required to take whatever you're telling the control logic to do. It synthesizes it into the type of functions that are available within that particular FPGA, and then prepares a bit map which will be loaded into the FPGA itself to actually implement those particular functions.
What was that one with the parentheses? Was that an error or just something there?
What's that?
The one with the parentheses on the...
Oh. If it's an if statement, if this is true, then do these things.
1, 2, 3, 4,
The bullets there,
5.
one was a 1.
Look at the bullet.
The red bullets.
Oh, that's a mistake on my part. I'm used to using chalk on a chalkboard. I don't draw those on a chalkboard. This is the user interface. It uses a Texas Instrument little microcontroller. It's 16 bits. It runs at 16 megahertz. It has 32 kilobytes of onboard flash memory, which means it can be reprogrammed. It has 1 kilobyte of RAM, which means it can store up to 1,000 user parameters if that's what you want to do with it. It has an EEPROM out here, which is for non-volatile storage of user parameters. If you've set a frequency, or you've set a pulse time, or you've set a chirp that you want to do, it'll store that information so you don't have to enter it every time you turn the power on. This microprocessor can be reprogrammed by the user. This is Texas Instruments. They provide all the software you need to take the program that you write. I write in what's called C because it's easy for people who aren't really professional programmers. And once again, it's just logical statements. This was part of a real-time clock. If the count reached half a second, because this real-time clock actually interrupts itself every 10 milliseconds, if the count reaches half a second, or it's greater than, that allows for some error if you've got an error somewhere, then it resets the half-second count to 0. It increments a half-second count by 1. If you're going to do any delay, maybe you're going to blank the display because you want something to blink at the user to remind him that there's something he needs to do. Or if he's pushing the push buttons, then it will allow him to hit the push button, allow the push button to settle, because every switch will have momentary open and close as it's bouncing. They're semi-critically damp, but they do bounce. Yes? 5 minutes. 5 minutes. Oh, okay. Darn. All right. And then once all that goes through, if the count of half seconds is equal to 2, then we count seconds, and we increment a seconds counter, and then we can do minutes, hours, days, months. Anyway, it's very simple stuff, easy to learn. This is a simplified picture of the MOSFET bridge. These are new gate drivers. The problem with the MOSFET is you want to drive the gate very hard, meaning amps of current, so as you get very fast response times, because the gate has a capacitance. These are the MOSFET switches. There's a diode across the MOSFET because when in the reverse mode, you know, as this inductor may be discharging through that diode, the diode has less voltage drop than the intrinsic diode, which is actually part of the MOSFET structure. So I put those in there to increase the efficiency a little bit. There's an inductor on each half of the bridge connecting to the piezo actuator. So this is a balanced connection, balanced 2-wire connection to the actuator. And these are just the gate drive numbers, 1, 2, 3, and 4. And that's replicated 3 times. Now in the actual design, I have paralleled 3 transistors, because if you want to have fast switching speed, you have to worry about L di dt. The inductance of the lead times the rate of change of your current and the amount of time. And so what I've done is I paralleled 3 of them, so we now have 1/3 the di dt on each transistor, so it essentially sped up its turnoff process by a factor of 3. So what happens is, if there's a voltage here on what's called the source lead, and when it's turning off, that's going to be a negative voltage, so the gate may be connected here to 0, but the source is down to -4 volts. The gate thinks it should still be on. So if the transistors are still be on while it's switching, it's just burning up useless power. So that helps speed up the operation. I'm using new silicon carbide transistors over the traditional silicon. The advantage of silicon carbide, it has 10 times the dielectric breakdown voltage, it has 3 times the band gap, it has 3 times the thermal conductivity. That results in a higher breakdown voltage, a lower resistivity, so a lower on resistance, a higher temperature of operation. The electron mobility is a little bit slower, but we're not worried about that at 2 megahertz. Has faster switching speeds, but it does require greater drive voltage, but it has much lower interelectrode capacitances. I've compared, Cree makes a silicon carbide MOSFET, Vishay makes a standard silicon MOSFET. As you can see here, the Cree is good for more current, more peak voltage, much less resistance, 0.28 ohms versus 1.2 ohms. The input capacitance is 1/20th that of the traditional silicon part. The output capacitance is 1/40th. And the reverse capacitance, which occurs between the drain and the gate, which is one of the things that slows down the switching speed, is down to 2 picofarad. This is an illustration of the MOSFET turnoff. When you tell the device to turn off, it has a little bit of speed reduction, because as it's turning off, the current will go down slightly because it's an output inductor that maintains the current, and the MOSFET will be up to the supply voltage and still be drawing almost the maximum drain current. And then at that point, the drain current slowly falls off as the gate discharges through the driver. So to maximize the speed and reduce the switching time, you want to have that time from T0 to T2 be as short as reasonable. Now there's always a compromise in everything. It takes a lot of current in a short period of time to achieve that. This is an estimate of the bandwidth of the current device with a 200 kilohertz anti-aliasing filter. This is Carson's rule for frequency modulation. I'm going to kind of push it a little bit. It's made for FM transmissions where you don't have a huge deviation. But he said, and this is back in like 1915, so it's 100 years ago, he said only the first sideband of an FM transmission is crucial. To actually calculate the sidebands, you need Bessel functions, which is beyond the need for what I'm doing. So I'm going to rearrange the terms. Here the bandwidth is equal 2 times the deviation of your primary frequency plus the modulation frequency. So what I'm saying is the modulation frequency is going to be the bandwidth divided by 2 minus the deviation. Now for Jim's present device, we'll say he wants to go from 40 kilohertz and he wants to chirp to 50 kilohertz. Now if he wanted to do that quickly, now the problem here is that means his deviation is 10 kilohertz because he's gone from 50 kilohertz from 40 kilohertz. His deviation is 10 kilohertz, but his available bandwidth is limited because he's only got 40 kilohertz to 0. but you can't go below DC. So we'll say it's 40 kilohertz, so we'll double that because it's got plenty of headroom on the other side. So we'll call it 80 kilohertz. So he could modulate his 40 kilohertz frequency at a 30 kilohertz rate, and this amplifier would amplify it. Now in a newer device, he may be using a frequency of 100 kilohertz, want to chirp to 120 kilohertz. So now we've got much more room to work with. So his deviation is 20 kilohertz. His available bandwidth is now 100 kilohertz to 0 and plus 100 kilohertz. So that's 200 kilohertz, which is our filter. So he can take that 200 kilohertz minus 20 kilohertz, and he has 80 kilohertz. He could modulate his 100 kilohertz signal. So I understand now he's only doing 2 kilohertz per second, so right now we're not going to run into that problem. I think the turn on and turn off may be an area that needs to be examined, which will certainly be faster than a few hertz per second. This is something I've lashed together from experiments. This is capable of 7,200 watts power. It's limited by dissipation because I didn't put fans on the little heat sinks.
David, could you summarize? We're out of time.
Oh, okay, darn. All right, well anyway, you can see it's, this whole crude apparatus is 18 centimeters wide and maybe the same long, but that includes a signal generator and a bunch of other stuff, which is doing other things. So I want to talk a little bit about ground currents. The leads should be shielded because they'll be high voltage. There'll be lots of switching noise on them. If you ground both sides of a shield, then you're going to have any current flowing through the ground. Then you get this ground loop current that flows in the shield, which could disrupt the voltages on your device under test. The conclusions are linear amplifier is physically large. It's inefficient. It's 70% theoretical for a sine wave. But as I say, I've measured it 23 to 35%, and that's at frequencies lower than what Jim is going to be running. It requires a matching network, which could be large. It could be 30 centimeters cubed per watt. Now, the one problem on a matching network is when any variables change, you've got to readjust the matching network if you want to maintain the same power flow. On the digital amplifier, it's physically small. It's about half a centimeter cubed per watt. The efficiency is 90 to 95%. It's a large bandwidth. There's no adjustments required, and it's user programmable functions. And that'd be it.